All right, welcome to section 11.1. This is the first section of the course. The book titles this Cartesian Coordinates in Space, but I'm going to sort of give it a slightly different introduction, which is, or title, which is, let's say, Introduction to 3D. So the reason for this, like a little intro to the intro, is that before Calc 3, basically everything happens in 2 or fewer dimensions, right? So before Calc 3, everything is in 2D, or I guess 1D, like on a number line. So in Calc 3, we need 3 dimensions. So this first section is to basically set the stage. Draw some pictures, understand how we're arranging our axes, things like that. So, to start with, let's say, let me call this, let's say moving from 2D to 3D. So we move from 1 dimension to 2 dimensions, right? We start with a number line. This is 1D. And then we go to 2D. And we get an axis, or a pair of axes, really. So here we have an x-axis and a y-axis. Back over here, traditionally, we just have an x-axis. So for 3D, we need to add another axis. All right. So, and it needs to be perpendicular to the other 2. So we'll say we need to add an axis which is perpendicular to the other 2. So, it's tempting to say, like, well, let's just go straight up. But that really doesn't work visually. So, we could do, like, this an idea. Like, it doesn't work, at least without some rearrangement of things. So a z-axis up, out of screen. This is hard to visualize. So instead what we'll do is we'll take a different approach. We're going to rearrange the x and y axis in sort of a 3-dimensional context, and then introduce a z-axis. So the idea is correct, but we need to draw this in 3D in a way that makes it manageable. So we'll redraw the x and y axes. So what I want you to do is I want you to imagine, let's say, the xy plane. So I'm going to think of that as a rectangle. Like, it's not really a finite rectangle, but for the sake of argument, think of this guy as x and y axis. Try and make these pictures nice. So I'm going to put this in a 3-dimensional context and make it like the top of a table. So let's say like a tabletop. So to do this, I'm going to be a little sneaky. All right, so you can sort of imagine the top of a table, and you can think the table's got some legs down there, and there are my axes. Now, it might be tempting to make the y-axis like the one that goes front to back and the x-axis left to right, but we actually won't. What we'll do is we'll make the x-axis come forward and the y-axis go to the right. The reason for this is we want the places where x and y are positive to be in front. Right? So this makes positive x and y in front. Right? Versus if we did something like the following, right? We won't do this, but this is just so you can see. If I did, it's really tempting to do this, but then positive x and y's in the back, and I don't want that. So to do that, I rotate this like 90 degrees this way, and we get the picture that we want. So this is the picture, let me circle this, that you want to sort of have in your head. So then what we'll do is we'll get the z-axis, we'll create a z-axis that goes vertically. So we'll then introduce a vertical z-axis. So in other words, if we go back and we draw this table again, and what I'll do is right now is I'll draw it without the legs. The reason for having the legs and thinking of it as a table is it gives you sort of a sense of perspective. Everybody knows what a table looks like. So, but we don't really need the table. So there's the z-axis. And this z-axis is perpendicular to both of those. It's like literally sticking straight out the top of the xy plane. So now when we have this, we can do things like plot points, look at planes, things like this, right? So now 3D space. Now, before we worry about plotting points though, what I want to do is I want to redraw these axes without the table and then draw another couple of planes just to give you a perspective of what's going on. So let me clear the left side of the screen and then redraw a little bit of this. All right, so let's say here are the axes without the table. So this is typically what we'll draw. Now the reason I don't start by drawing this is because having that table in your head can give you a solid notion of what's going on. Whereas if I start with this picture, it's kind of hard to see visually. Like some people have a better, seems like some people have a better three-dimensional sense of things than others, or some people are just more used to it, or you've seen it in other classes, whatever the case may be. But this picture can be confusing to people at first. But generally, once you have an idea, you can sort of visualize that the x and y axes, they make up a horizontal plane, and the z-axis is straight up and down. And I'm going to try and make a habit of putting arrowheads in the positive directions. So now before we plot any points, just to help us see what's going on, just to make a little note is that, you know, we have this xy plane that's sitting like the tabletop. So besides the xy plane, we have two other planes that appear. So let me redraw the xy plane. Just so we see, this was our xy plane. And the xy plane has the x-axis and the y-axis in it. We also have the xz plane. So the xz plane contains the x-axis and the z-axis. So there is our x-axis coming forward and our z-axis going up, and the y-axis goes to the right. And we also have the YZ plane. So let me draw that on the right-hand side. So we'll say, and the YZ plane. This is the easiest one to draw because really it's the screen. Or in a classroom, it's the blackboard. This has the y-axis in it, the z-axis in it, and the x-axis sticks out in front and behind. Now, if you draw all three of these together, I like drawing sort of all these before we even plot any points because it allows us to wrap our hands a little bit around what's going on. So what we'll do is actually, let's do this in different colors. This might be a giant headache, that's right. So we've got that guy. Actually, I'm going to completely and utterly not do this in three different colors. I realize this will be a nightmare if I try and do this in an organized fashion. So I'll just do it in one color. It's hard enough in one color, let alone in as a reasonable picture. So this is all three together. Now, little note here, if you look at these, Now these planes go on and on forever. They go up and down forever, left and right forever. They extend outwards into space. So these divide space into 8 subsets. So these together divide space into 8 subsets. These subsets have a name. These are the 8 octants. Now, in terms of which is which, the only one that you can actually say, like, this is such and such an octant is the first octant. The first octant is the stuff right in front here. That's the first octant. In other words, there's no standard for what the second octant is or the third octant, but the first octant, there is, it's this one. And this is, the reason this is useful is this gets used a lot to describe areas of space. This is where all of x, y, and z are greater than or equal to 0. This is why these are organized this way. This is like you can either say greater than or equal to 0 or greater than 0, but it's the axes are organized this way so that the positive stuff is all sort of front and center, like on a stage. If the axes were labeled differently, rather, if the x-axis went backwards, then the first octant, the positive place would be somewhere else on the arrangement. It would be a bit confusing. So this is sort of the best way to do it for that reason. So take a look at these pictures for a second, get this sort of embedded in your head and how these work, because what we want to do next is we want to learn how to plot points in space. And it'll help if you have a solid understanding. We'll draw the tabletop analogy one more time, but otherwise we'll just plot a few points and go from there. So I'm going to clear the screen off completely and go to that. So 3. Plotting points. So clearly you can probably guess to plot a point in 3-dimensional space on the 3 different coordinates, x, y, and z. So we'll need 3 coordinates, x, y, and z. And so the way to do this, I mean, there are a bunch of ways to do this, but like a good introductory way, maybe let's say as an idea, is first plot x and y, then measure up and down for z. So what I'll do is I'll do this, like, I'm going to really draw this out for one example. And typically we won't do this. Typically your pictures don't need to be beautiful. They don't need to be perfect. They just need to be reasonable so that you understand what the heck is going on. But it's worth really belaboring one, just so that you sort of understand what's going on when we draw these pictures. So let's plot, because there are a lot of nuances that if I just sort of start throwing points down, you might like stare at them wondering why something is true. So let's plot the point, say 2, 3, 5 is a good one. Now, going back to this tabletop can help. And not only that, but drawing a grid on the tabletop can help. So first, let's draw the XY plane with a grid. Let's say like the tabletop. And so I'm going to do this in a light color so that it's a little easier to figure out what's going on. So I'll do like a light green for this. Not too light. I'll draw a few pictures for this as we go. I'm not going to worry about the z-axis just yet. So there's the 0, 0 right there. There's the x-axis. There's the y-axis. And so for a grid, you can see that the parallel lines for the grid, those go at an angle because it's like you're looking at like a grid that's on a table that's lying perpendicular. And so if we start from the middle, right, there's the origin right there, and I'm going to go 2 units in the x direction, that's this way, and 3 units in the y direction. So this right here, this is the point. Like if we haven't done any z's, let's just say this is x equals 2, y equals 3. So really, if I imagined a z-axis, it would be 2, 3, 0. So for 2, 3, 5, we need to go up 5. Now this is where it can be a bit weird, I don't want to say confusing, but maybe confusing is the right word. So what I'll do is let me redraw this. I'm not going to redraw the entire grid because you can always refer back to it. I'm not going to draw the negative z-axis for now. I'm just going to go, I'm going to take what we just did. I'll draw it in blue. This was 2 units and 3 units. So that's the picture from before, right? So now here's the thing. I need to get some sort of scale on the z-axis. So 5 units, I might say like my tick marks, maybe a 1, 2, 3, 4, 5. So it might be tempting to go straight up to right here. But that actually doesn't really work, because if you think about it, like there's a sense of perspective going on. So what I need to do is I need to be 5 units above the blue point, right? So let me erase this question mark for a second. What I'll do is off to the side, right? Let me go, this is sort of the distance between the origin, the middle, and 5 units up. So what I'm going to do is I'm going to go 5 units above that. So that's probably about that distance. And then what I'm going to do is I'm going to put a point right there. This is 2, this is 3, and this is 5. Now, if that's a bit confusing, that's okay. I'm going to draw one more picture that can sometimes really help. When I draw this, very often people will look at it and there'll be this sort of this moment of, oh, obviously. But this is sort of the idea. Is I follow this on the xy plane first, and then I go in the z direction accordingly. And again, remember, this is the z direction. And so what I'll do is I'll say this, drawing a box can help. Now, if you're not sure what I mean by drawing a box, that's perfectly okay. You'll see in a second. So what I'll draw is I'll draw a box, and then hopefully when it all comes together, it'll all make sense. There's a box. The box has a certain size. So these are the axes appearing, and they meet at the back lower corner of the box. This is the x-axis, this is the y-axis, this is the z-axis. This box now is 2 units forward, 3 units this way, and 5 units up. So what that does is that tells us where our point is. This point right here, that's our point of interest. This is 2, 3, 5. Now, for what it's worth, it can really help the perspective too. Let me draw some other points on there. This point there's no y direction. This is the point 2, 0, 5. Back here, this is the point. There's no x direction. 0, there's no x distance. 0, 3, 5. This is the point 0, 0, 5. So this picture can be helpful because it can help you see the top of the box. Everything's at a height of 5, but you have to take the perspective into account when you look at this, or else it's really easy to think that the front dots are lower than the back dots. Like, they're not lower. They're lower in a 2-dimensional sense. They're the same height with a 3-dimensional perspective. So I'm not going to be drawing a lot of boxes, but this one picture can really, really help people see what's going on. So what I'll do is I'll draw a couple more points, and then we'll talk about some things measuring distance between points, and then we can talk about our first object in three-dimensional space. So let me clear off the screen, draw a few more points, go from there. So we'll just say a few more points. And I'll draw these fairly rapidly, like without drawing too much busy stuff. But we'll draw 3, let's say. We'll do the origin because it's an easy one. I'm going to give these letters just capital letters so I can mark them nicely. Then we'll do Q, could be, say, -2, 3, 5. R will be, say, 0, -4, -1. And S could be, say, 6, 1, -1. I'm just going to, what I'll do is to keep us from having to do too many pictures, I'll draw all of them together on one set of axes. We'll take this sort of slowly, hopefully, so we can see. The easy one is the origin, of course. This is P right here. Right there. 0, 0, 0. So for Q, I go -2 in the x direction. So that's back here. I go 3 in the y direction. So that would be like here. And then we go 5 units up. So there's no sense of scale here. So maybe we could just, play a guessing game here. This would be our Q. Just take a second. I'm going -2 in the x direction. So that's back 3 units to the right. Again, that tabletop center perspective's there, and 5 units up. And again, it's only 5 because in some sense I have this idea in my head that maybe like this is, 1, 2, 3, 4, 5. And so you can imagine a box in that backside, in that back octant. So then we've got R, which is 0 in the x direction, so no forward back, -4 in the y direction, and 1 unit down. We've got S, which is 6 units forward, way out here, 1 unit to the right, and 1 unit down. Those are our points, right? Now, something to consider, we're not going to be plotting a lot of points. Really, the reason we're doing this is so that when we start drawing objects, spheres, paraboloids, we'll be doing a lot of things as the course goes by. It'll really help to have a sense of what belongs where in XYZ space. So don't, obsess if you're struggling to like look at where these points are exactly. It can be confusing, and that's okay. But just doing a few points can help you get a sense of like what's up, what's down, what's left, what's right, what belongs where. So next to last thing I want to mention is distance between points. So the last couple of 2 things here are pretty straightforward because they follow fairly immediately from Calc 1 and Calc 2. So if you recall, in Calc 2 or Calc 1, or really in pre-Calc, we have 2 points. This is in 2 dimensions. Let's say x1, y1, and we have q equals x2, y2. The distance between them. There's a bunch of notation for this. One notation, one that we'll use, it looks like an absolute value. This doesn't mean absolute value. It's just a notation for the distance between P and Q. This follows from the Pythagorean theorem. I take the difference of the x's squared plus the distance from the y's squared. Take the square root. This is the Pythagorean theorem. So when I move to 3 dimensions, I simply have another term. Right? So in 3D, it's really the Pythagorean theorem happening twice, or the Pythagorean theorem in 3D think about it however you like. So if you have these 2 points, then the distance between them is distance between PQ. So it's the exact same formula, except it gets a Z. And notice it doesn't matter if you do x2 minus x1 or x1 minus x2 because you're squaring. It doesn't matter if you do the x's then the y's, or the y's and the x's. Doesn't matter if you do the z's first or last because you're adding. That's it, the Pythagorean theorem again. And so, for example, the distance between, say, 1, 2, 3 and 8, 0, 4 is simply square root, and I'll do them in the same order that I listed them. 8 minus 1 squared plus 0 minus 2 squared plus 4 minus 3 squared. And I'm not a big proponent of simplification, so don't obsess too much about this. But in any case, this is 7 squared is 49. This is negative 2 squared is 4. This is 1 squared is 1. This is the square root of 54. So nice and easy distance between points. The only reason I really mention it is our first formula. It was one reason, and also because it leads to the last thing that we need to give, which is the equation of a sphere. And so to give the equation of a sphere, let's harken back to the equation of a circle in 2 dimensions. So again, let me, this formula that we have for distance is easy to remember. Let me clear the screen off. Look at circles, move up to spheres, look at some examples and draw a picture. That'll be our first really interesting picture of something that is not a point. So we'll say, let's say circles and spheres. We also need to look at disks and closed balls, but we're going to put that as we go. Let's look at circles and spheres. So, just a reminder. So in 2D, a circle centered, oops, let me spell that right, at x0, y0 with radius capital R. So if it's centered the origin, it's just x squared plus y squared equals r squared. But if it's not centered the origin, we shift it. So hopefully this rings a bell. So that's this guy. And for example, say x minus 2 squared plus y minus 3 squared equals, say, 5 squared. I'll put 5 squared now instead of 25 just because it makes it easy. And I go over 2, go up 3. And then I sort of measure a radius of 5. I'm just going to run over the picture there, that's all right. It's a terrible circle, no big deal. And that's our circle, nice and easy. Right? Now, this is a circle, so I just want to add a term to this. Right? This may not be a definition that you're used to. Right? So a disk centered at x0, y0 with radius R. This has inequality x minus x0 squared plus y minus y0 squared less than or equal to r squared. So just to really emphasize the difference between these, let me redraw this equation from above, from up there as an inequality. I won't make the picture too complicated. I'll just do this. The difference between these is that this second one is shaded in. So it's something that we need to keep in mind. And this can be a sticky point sometimes for students. Even though it's pretty simple, but it's really easy to get them confused, is keep in mind a circle. A circle doesn't include the inside, right? A circle is literally just the edge. right? Like the stuff that's inside, right? This is not the circle, right? It's an equation, so you have to be on the surface itself, right? In the lower example, the disk is the whole thing. It's filled in. It's like a circle is like the crust of the pizza, like an infinitely thin pizza crust, which isn't very exciting or delicious. But the disk, that's the whole pizza. So likewise, when we move to 3 dimensions, right, so in 3D, a sphere centered at x0, y0, z0 with radius r. And you can probably guess where this is going. All I do is I add in a z term. Now, let me draw a picture. Let me do one of these. I'm going to pick start at the same, and then we'll do, say, z minus 5 squared. And we'll say do equals, say, 4 squared, like 16. Right? So before we write about a disk, we'll draw this sphere. And so the way to draw this, right? So for the record, this worries a lot of people. You think that these pictures are hard to draw. So I would just say practice, practice, practice. Everybody gets good enough at drawing these pictures, right? The reason for drawing the pictures is not for me, it's so that you can draw pictures which are sufficient for drawing the mathematics, for doing the mathematics later. So when you draw your pictures, don't worry so much about, do I understand them? The answer is almost certainly yes. The real question is, when you look at them, do you understand them? Do you understand what's going on? So what I'll do for this is, first I'm going to draw is, I will do this. I'll draw some tick marks. That'll really help. And then what we'll do, first of all, locate the center. Right? So for the center is 2, 3, 5. So the center, we go 2 units in the x direction, 3 units. This would be 2, 3 would be right there. We'll go 5 units up. So 5 units up takes me about right to there. So think of the box that we had earlier. That's that corner of the box, if you like. Okay. And then what I do is I need to draw a circle that has radius. What I'm going to do is I'm going to draw a circle that has radius 4. So radius 4 will almost get me down to the xy plane again. It'll probably get me to about here. So I'll draw this. Again, doesn't need to be perfect. Now, if I stop there, looks like a circle, doesn't look like a sphere. So there are a variety of ways you can give this some depth. What I typically do is I typically will draw like an equator and a dashed equator on the back. I'm not saying that you have to do this. All I'm saying is, like, for me, for all the years I've been doing this, this is what I draw that makes my brain go, oh, that's a sphere. Right? And so probably, it might be a good habit to do it the way I do it, just so we're all on the same page. But basically, if you look something that looks spherical, you're fine. It's not a big deal. So this is typically what I'll draw. But again, as long as you draw something and you understand it, then you will be fine. Right? So a ball then, this is sometimes called a closed ball, but a ball also works as well. Let's say centered at x0, y0, z0. This radius r has equation, so you can see where this is going. It's just going to become an inequality. Just like that. And so the only difference is when I draw these. So for example, the above would be x minus 2 squared plus y minus 3 squared plus z minus 5 squared less than or equal to 16 or 4 squared. So the only difference when I draw these is typically I'll just draw it without the equator at the back. Again, this is just for me. It helps me figure out what's going on. So let me draw one of those. Let me just clear the left side of the screen off and redraw this. And write down what I'm just saying. So I'll say this. For this, I would draw. I'll sort of just do this fairly straightforwardly. I would draw basically the same picture. This is exactly the same picture as the left. Let me just feel. And I just would not draw the back. I would draw the front. And again, this is just me. This is what I draw. So my brain goes, hey, look, that's filled in rather than not filled in. But it's totally up to you, like how you draw this. It doesn't need to be a work of art. It just needs to communicate the idea well enough to you. So the final comment I want to make, and this final comment doesn't just apply to spheres as well. It applies to every single equation that comes up in the course, but it also applies to equations you've seen before. And that is the equation, like the equation of a sphere may not look initially like the equation of a sphere, and you may need to manipulate it, right? So like in Calc, let's say 1, or even in pre-calc, I'll just say Calc 1 for now. The equation something like y plus x squared equals 3 is a parabola. Because it's the same as y equals negative x squared plus 3. Like you rearrange it to make it familiar. Right? So likewise, let's say not and, but let's say the equation of a sphere may not be immediately obvious. Now this will go for lots of things that we draw. So let me just end with a specific example. Let me clear off the right-hand side of the screen and just work through an example really, really easily. So something like this. Consider, let's make this really kind of messy. Let's say x squared plus y squared equals, say, 4 minus 2x minus z squared minus 6z. So it doesn't look like a sphere. It's not written in a familiar way. Although you do see the x squared and the y squared and the z squared, maybe rings a bell, but you also see the x and the z, right? If we rearrange, we get, and sort of rearrange and put things together. So I'm going to put x squared plus the 2x, and then the y squared will be left alone. There's no y's to go with it. And then I'm going to have a plus z squared plus 6z, and leave the 4 on the right. So then we complete the square. So I'll write CTS for complete the square on x and on z. So remember how this works. Take half of the coefficient, which is 1, and square it. The y I'm going to leave alone. For the z, we take half the coefficient, which is 3, and square it. And then we need to add that to both sides. We need to add the 1 and add the 9 to keep the equation balanced. And then what we'll do is we'll sort of factor these. This will be x plus 1 squared. I'm going to write this as y minus 0 squared. And z plus 3 squared. You don't need the minus 0, of course, but and over here we have 14. But it can help. So now we see this is a sphere with center -1, 0, 3, and radius square root of 14, because the right-hand side is the square root of 14 squared. So just to realize that things are not always as they seem, they may need the rearrangement. So that's it for that section. So I'm going to end that here.